Okay, I'm gonna go over the rest of the things we need to know about series in this one. So, honestly, before this ratio one, I should have started with what an alternating series is, but I forgot to do that. So I'm just gonna go over it right now. So an alternating series is usually just one with that has like a negative 1 in front, like this. Negative 1 to some n power. It could be n or n minus 1. But as long as it's got that negative 1, then you can pretty much clock, okay, yeah, that's an alternating series. So an alternating series is a series that, sorry, is one that, well, alternates between positive and negative values. So if we start at n equaling 1, then we have to have this exponent be n minus 1. But if this were like n equaling 0, then you can just have this as n. Oops. Okay. Oh wait, I forgot to write the rest of the actual series. And then let's just say the sequence is like b sub n. So essentially what will happen to this is it's going to start out positive because you put in a 1 here and you get this this equaling 0. And anything to 0 power is 1. So it's just 1 times b sub 1. But then you put in a 2 here and it becomes negative 1 to the first power, which is negative 1. Yeah, and then it's negative 1 times b sub 2. So you see how this changed from positive to negative now? And then it's going to keep alternating, because if you insert a 3 there, you're going to get negative 1 squared, which is positive again. And then you insert a 4, you get negative 1 to the third power, which is negative. And you just keep going. So it changes from negative to positive to negative to positive, or it's changed from a positive to negative to positive negative, for all of infinity. So yeah, that's alternating series. And there's actually a test that goes with that called the alternating series test. Alternating series test. So this thing has two conditions that you have to satisfy. First, b sub n plus 1 has to be less than b sub n. So as you add more, the numbers that you add have to get smaller. So like b sub 2 has to be smaller than b sub 1. B sub 3 has to be smaller than b sub 2. So that's what this is saying. So, aka, it's decreasing. And the second condition is that the limit as n approaches infinity of this series has to equal 0. And if these are both true, then it is convergent. So, what this looks like if you had it on a graph, like say this is our number line, and we start here. So this is 0, and this is s sub 1. So s sub 1 means the sum of the first number. So that would be like this distance here, because this distance is b sub 1. And because it's decreasing, the distance that you go back, because it starts positive and then it becomes negative, so now we're subtracting, so we're going this way. But we don't go all the way back to here because the function is decreasing. So this is b sub 2, and it's a smaller number than b sub 1. So we only go back this way, so it's negative, right? And then this is s sub 2. So s sub 2 is b sub 1 plus b sub 2. Or I suppose b sub 1 minus, since that's a negative there. And then you just keep going. It alternates, right? So now it's positive, and you go back here. But it's not all the way back here because the function is decreasing. So now this is s sub 3 because you're adding up the first 3 terms. And then you go back. This is b sub 4. It's subtracting because you're alternating. So now this is s sub 4. And then you just keep going back and forth until eventually you converge to this number, and that's s. And that number you converge to, yeah, until you converge to a number. Okay, so that's how you can visualize the alternating series. We need another page. Okay. So now we know what an alternating series is. Let's talk about the alternating series error bound theorem. Okay, that's a lot of words, but alternating series error bound. So this is us finding the error of a series. Okay, I'm gonna write what the theorem says here. Theorem. So, okay, so it's saying if we have a series that converges, if we have an alternating series that converges, that is also positive and converges, then the error bound of the series, the alternating series error bound, is this notation. So it's the absolute value of r sub n, which is the same thing as writing s minus s sub n. So this is equal to s, by the way. The series is labeled as s. Greater than or equal to b sub n plus 1. So essentially, this value has to be less than the next number in that sequence. Okay, so let's see if I have any questions. Yeah, okay. So let's do an example. So I have this series, negative 1 to the n minus 1 times 3 over 2 to the n plus 1. And what we want to do, we want to find s sub 6. So this means the sum of the first 6 terms in the sequence, and use the alternating series error bound theorem. That's so much to write. To show it differs from s by a value of less than 3 over 1000, which is the same thing as 0.003. Okay. Here, let me separate this from, let me separate this from the whole thing a little bit. Okay. So what the alternating series error bound theorem shows is how far away your estimate of s is from the actual value. Because we can't add up an infinite number of terms. that are in the sequence. We can only add up a finite number. So this this error-bound theorem tells us how off we are from the actual value that it converges to. So like in this case, we're going to add up the first 6 numbers, and we're going to see how much those first 6 numbers differ from the actual value of the series. And we want it to show that it differs by less than 3/1000ths of a value. So that means our estimate is within 3/1000ths of the actual value that the series converges to. So that's what this is showing. So the way we do that is we want to add up the first 6 values in this sequence, because that's the first thing it asks us to do. So as sub 6, so what we're going to do is we're going to plug in a 1 into here, and then we're going to keep going up to 6. Yeah, because remember, s sub 6 is equal to b sub 1 plus b sub 2 plus b sub 3, blah, 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 all the way to 6. And this number is the number that, well, that next number in the term, but also what number you're plugging in. So we start at 1, and we increase by 1. So -1 to the 0 power is just 1 times 3. So on the numerator we have a 3. And then plugging a 1 here, we get 2. Plugging a 1 here, we get 2. So that means we have 4 on the bottom. Okay. And then we're going to plug in a 2 here. So that makes -1 to the first power, which is negative. And so that means the numerator is going to be negative. And then we plug in a 2 here, we get 3. Plug in 2 here, we get 4. So 3 times 4, we could just cancel out this 3. So it becomes 1/4. So, oh, oops, 1/4. And then we plug in 1, okay, this is 1, this is 2. Now we plug in a 3 here. So that gives us -1 squared, which is a positive 1. So a positive 3. And then plug in a 3. 2 times 2 is 4. 4 times 2 is 8. Times 4. 8 times 4 is 32. So that's our third term. And we're just going to do this all the way up to 6. So, anyways, just keep plugging it in. I'm just going to write the numbers here for, because you get the point by now. Six. Okay, so this is the value of s sub 6. And we don't even need to bother writing out the whole thing, because that's going to take forever. I mean, like, adding all of these up. Okay, and then we want to show that the error is less than 3/1000th. So I'm going to take this format of the error. Less than. Okay, so s sub 6 is the 6th, like, adding up the 6 terms. Okay, sorry. So now we want to show that this is less than b sub n plus 1. So that means the next term after the 6th. So this would be the 7th term. So after you add up the first 6 terms, we want to show that the first 6 terms have an error of less than this value. So to show that, we have to find the value of the 7th term in the sequence. And I'm just going to cheat and tell you what it is. It's 3 over 1024. And all you're doing is you're just plugging a 7 into there. In here. In here. Okay. So this is just our notation for showing an error. So this is like the actual value of the series, and this is the value of the series that we found. So we plugged in a 6. So ours there is S sub 6. So why don't I write that actually? Connect. This is S sub 6. Yeah. And to show that the error is less than 3 over 1000, we have to find b sub, it's n plus 1, so our n is 6, so that's b sub 7. So this is the value of b sub 7. That's an ugly arrow. That's the value of b sub 7. And this number is less than 3 over 1000. So that's how we know that it is true that the S sub 6 differs from S by a value of less than 3 over 1000. Okay. So that might have been a little confusing, so just to recap. We found S sub 6. That's the series of all these numbers added together. So this is b sub 1, b sub 2, b sub 3, b sub 4, b sub 5, b sub 6. Added all those together, that's the series of the first 6. And then we want to show that the sum of the series of the first 6 is less than 3 1,000ths of a number away from the actual sum of the series. And to show that, we have to take the 7th value, that would be like right here, of the series, so the 7th term in the sequence, because this number is, remember, it's b sub n plus 1, b sub n plus 1. So this is the n, this is n plus 1. So this is the next term in the sequence. And this next term is smaller than 3 over 1000, so that's how you know that, yes, this is true. It differs from the actual value of S by a value of less than 3 over 1000. Okay. Did I talk about root test? No, I didn't. Okay. Okay, we're going to do root test next. So root test we haven't used very much, but it's still one that you need to know, because what if you do end up having to use it? So root test is good for combating series with the powers of n, because those can be very annoying to deal with. So we take the limit as root n, and what's inside is in absolute values. And if the limit of this is less than 1, then you know the series of this sequence is absolutely convergent. So the way these values go and the way you interpret it is very similar to the ratio test. Yeah, so that makes it absolutely convergent. And if it's less than 1, I mean greater than 1, then the series is divergent. And then, like the ratio test, if it equals 1, then the root test is inconclusive. Okay, and I'm just going to write that. So, 3 over 1000 plus 1 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 over 1000 plus Okay, let's do a practice problem with the root test. So, we're going to take this series. Oops. Let's see which one. Let's just do this one to start out. Equaling 1. Two, oh right, 2. Okay, so this is our series. And you see it has a power of n here. So this is really good for the root test because the root test takes the square root with square root, the nth root, not the square root, the nth root. So it essentially cancels out with this one. So what we want to do is we just want to put that in the form that we see right here. So nth root of our series, and our series has the absolute value. Oh wait, I forgot the nth. There you go. Okay, now it's easy because this nth root cancel out with that nth power. So we just have the limit of what's left on the inside. So 2n plus 3, 3n plus 2. And then now we just take the what is it called? The limit. And these both have a degree of 1, so we just take the ratio of the coefficients with it, which is 2 over 3. And 2 over 3 is less than 1. So we can say the series is absolutely convergent by the root test. So whenever you're writing these answer like sentences, what you do is you just rename the series. You tell them what you found, absolutely convergent, divergent, whatever, and then how you found it. Okay? So that's how you do that. That's an example of our root test. Okay. Okay, let's see if I have room up here. Okay, so back to these series. So there's another series actually, and it's called a power series. So the power series looks like this. It's going to be a summation like all series are. Start at 0, a sub n times x to the n. So now these series have x's involved in them, whereas all of our other series, they only had n's, no x's. See, n's. So now we're including like an actual variable into the equation. Because these aren't really, I mean, they're variables, but not really, because they equal these numbers. So it can look like that, or it can be x minus c. And then this number c is the center of the power series. So, with power series, sometimes they'll ask you for the center, where the center is. So if you don't see anything like transforming the x, it's like there's no like minus some number or plus some number, then the series is just 0. So the series, I mean the center is just 0. So the center of this series is 0, but the center of this series is x. Okay. Okay. And one of the properties of this power series is that there are only three outcomes for a power series. So a power series can converge only when x equals c, or it can converge for all x, or it converges on some and diverges on others. So there could be a positive number r such that the series converges if x minus c, so the absolute value of that is less than r, and diverge if the absolute value is greater than r. So this r is the point that the point at which the series changes from like converging to diverging or diverging to converging. And this number r is called the radius of convergence. So this is the radius of convergence. So in some questions they'll ask you to find what is the radius of convergence. And all you have to do is you take a look at this power series, you take that, whatever's inside the argument of the n, put it in absolute value bars, and set it to less than r, because if it's less than r, it converges. Okay, so why don't we do a practice problem with that? Let me find one. Oh, and also, the r's for the first two cases. So in the third case, the r is going to be a number, but in the first case, where it only converges at one point, r is going to be 0. And if it converges for all of x, then r is infinity. And if it's the third case, then r is going to be one of those numbers, just some number. Okay, let's find a problem for this. Okay, I'm going to put it right here. So this is our summation. See, here's our x, 2n plus 1. And then 2n plus 1. That's going to be factorial. So we want to find where this converges, and then we can find the radius of convergence. And also, I forgot to mention, the interval of convergence is all the values that all the values of x for which the series converges. So yeah, just this could be your interval, all x could be your interval, just some x's, specific x's, like if it only converges for that can be your interval. So okay, anyways, you'll see in this problem. So oh, you know what, why don't I do another problem, because this problem converges everywhere. So let me write this one down. N factorial x to the n. So what we're going to do is we want to solve this using the ratio test. So we're going to ratio test this. So remember, for ratio tests, we replace all the n's with n plus 1's. So this is n plus 1 factorial, and x to the n plus 1. And then on the bottom, we just have our regular series, sequence. Okay, now we're going to solve. Just keep the limit there since I'm not ready to solve for that. So now, the ends are always going to be positive numbers, but this x, we don't know what number it is. And the reason the ends are always positive is because we start at 0 and just increase, so they're all positive. But the x's are a variable, so we don't know what x is. So whenever we solve this, we want to keep the x's in their absolute values. Oh, and we want to be able to cancel this number out with this. But the issue is that right now the n is stuck inside the factorial. But if we think about it, factorial is just the inside subtracting one number and you multiply it to that number. So this is a factorial times n. Well, here, I'll start like this. N times n minus 1 times n minus 2. So what you do with factorial is just you keep decreasing. So like 3 factorial would be 3 times 2 times 1. You just decrease 1 each time. So we can use that by writing out this first number, and then the rest would be the rest of the n. So do you see how I did that? This is the first number, and then it's n times n minus 1 times n minus 2. But like, this is just the factorial of n. So that's why we just condense it into n factorial like this. So we just multiplied it out by the first term. And then our x to the n, we're going to separate like we did before. Because remember, this is the same thing as x times x to the n times x to the first, because you add the exponents when you're multiplying numbers with the same base. And then we have our regular x n factorial and x to the n. And remember, these are in absolute value bars because we don't know if they're positive or negative. So now we can cancel out those. So what are we left with? Limit approaches infinity of n plus 1 times absolute value of x. Oh, okay. I did the wrong problem, but that's fine. So, as we can see, our x here is that x. And, so our radius of convergence is 0, because there's nothing like added or subtracted from that x. It's just an x. So just an x, then it only converges where radius is 0. That's a big 0. Okay. Oh, that's not the problem I wanted to do. Well, we're going to do the problem I wanted to do. Wait, actually, I can just highlight this and delete it. Or actually, I shouldn't delete it. I should just move it around. Okay, this can live like right there for now. I just need room to do this. Okay, so this is the actual problem I wanted to do. Okay, so once again, ratio test. Put it in absolute values, n plus 1 over just the regular. And remember, we can rewrite this as x minus 2 times n times x minus 2. So if we did that, oh, these 3's cancel out. And the x minus 2 to the n would cancel out with the x minus 2 to the n. So then we would just be left with x minus 2 in absolute value bars. So this limit is equal to absolute value of x minus 2. And that's because this limit is regarding n approaching infinity. But what we have in the argument is x. So the limit doesn't do anything to the x. And now, remember to find our radius of convergence, we want to set this equal to, as less than, or less than 1. Less than 1. Well, yeah, but you're always setting it less than 1. Oh, right, because, remember for ratio test to converge, it has to be, the n value has to be less than 1. So that's why we set it equal to less than 1. Not equal to less than 1, but we set it less than 1. And when you have it in this form, like nothing is like multiplied or divided to the x, this is just your radius right here. So we already know our radius is 1. You can I'm going to put it over here. But we still want to have this as less than 1 and greater than -1, because we want to solve for our interval of convergence as well. So now the reason it becomes these two is because, remember, this is the same thing as plus minus x minus 2. And when you make it a -1, you're moving the negative to the other side. And when you multiply by a negative, you have to flip the sign. But when it's just a positive, that you don't have to flip the sign, so it's just that, the less than 1. Okay. So then when we solve, we find that x is less than 3 and x is greater than 1. So this number tells us the interval that we converge on, for, remember, this third possible outcome. So our interval of convergence is 1 to 3. Yeah. And that makes sense because, okay, yes, I'm putting it all together now. Because our center is 2. Since you see how this is the center here, center. Okay, so our center is 2. And our interval of convergence is 1 to 3. And our radius is 1. So what this means is that this radius tells you how much up and down you go from the center. So if our radius is 1, that means we go up 1 from the center and down 1 from the center. And up 1 from 2 is 3, and down 1 from 2 is 1. So that's how they all fit together. Center, radius, convergence, interval. Okay. There are certain series that you should memorize, and they're in your notes somewhere. It's like that big fat sheet of paper that he had us glue in. It just makes your life easier if you have them memorized. I'm not going to write them down because that'll take forever, but okay, yeah, that's series.